In this lesson, we're going to talk about solving polynomial equations. And if you know how to factor, then you're really doing well already, including if you know how to use the factor theorem. When we solve higher order polynomials, such as equations that are degree 2 or higher, we make one side equal 0 and we factor the other side. And sometimes if we have a quadratic equation, we can use the quadratic formula. In this course, we're going to focus on common factoring first, using the factor theorem if we have something that appears unfactorable, using sum of cubes or difference of cubes where possible, and also using quadratic factoring methods or the quadratic formula if we have a quadratic that is not factorable. So suppose we're given this equation here, 3x times 2x minus 5 times x plus 4 times x minus 10 equals 0. Well, we already have one side equal to 0, and we already have the left side factored. That's amazing. So we just set each of these four individual factors equal to 0. So if 3x equals 0, then x is 0. If 2x minus 5 is 0, then 2x is equal to 5, or in other words, x equals 5 over 2. If x plus 4 equals 0, then x is negative 4. And if x minus 10 is 0, then x is equal to 10. And so we have a final answer of 0, 5 halves, negative 4, or 10. But it is nice, quite frankly, to put solutions in order from least to greatest. And we want to appear sophisticated, so we'll say x is equal to negative 4, or 0, or 5 halves, or 10. Now, what if we're given this equation here, 6x to the 4 plus 70x equals x cubed plus 57x squared? Well, we want to make one side equal to 0, and then we see an opportunity to common factor. We can factor out that x. Now, let's let f of x briefly equal 6x cubed minus x squared minus 57x plus 70. I'm using the notation f of x because it'll be easier to explain what I'm doing when I start using the factor theorem on this cubic. Well, we see that f at 1 equals 18, so x minus 1 is not a factor, and f at negative 1 is equal to 120, so x plus 1 is not a factor. So you may have guessed we're using the factor theorem here because we have a cubic and we don't know how else to factor it. F at 2 is equal to 48 minus 4 minus 114 plus 70, which equals 0. Since f at 2 equals 0, we know from the factor theorem that x minus 2 is a factor. Awesome. So we're going to use synthetic division. Our cubic was 6x cubed minus x squared minus 57x plus 70. So using synthetic division, bringing down the 6, 2 times 6 is 12, negative 1 plus 12 is 11, 2 times 11 is 22, negative 57 plus 22 is negative 35, 2 times negative 35 is negative 70, 70 minus 70 is 0. We see that 6x cubed minus x squared minus 57x plus 70 is really equal to x minus 2 times 6x squared plus 11x minus 35. Now, using quadratic factoring methods such as the crisscross method or decomposition, we see that 6x squared plus 11x minus 35 is actually 3x minus 5 times 2x plus 7. What this means is we can take that fourth degree polynomial that we originally let equal 0, and we can say that that's really equal to x times x minus 2 times 3x minus 5 times 2x plus 7. Now, since all those factors multiplied equals 0, that means one of the factors might equal 0. Well, if x could be 0, or if x minus 2 is 0, x is 2, or if 3x minus 5 is 0, x is 5/3, or if 2x plus 7 is 0, x is negative 7 over 2. And we get our solution. X is equal to negative 7 over 2, or 0, or 5/3, or 2. What if we want to solve this equation? Well, what we do right away, we say one side equals 0. That's good. And we see an opportunity to common factor out 3x, so we do that. Now, we've got a fourth degree polynomial, and we're going to try the factor theorem. We see when we plug in when we plug in an x value of 1 to this fourth degree polynomial, we get a non-zero evaluation. When we plug in an x value of -1, we get 7. When we plug in an x value of 2, we get 64. So far we're out of luck. But then when we plug in an x value of -2, we actually get 0. That means x plus 2 is a factor. So we use synthetic division. Now remember to include a placeholder of 0 where necessary. This fourth degree polynomial is x to the 4 plus 2x cubed plus 0x squared plus 8x plus 16. Now using that synthetic division, we see that we end up with a quotient of x cubed plus 0x squared plus 0x plus 8. In other words, x cubed plus 8. That means x to the 4 plus 2x cubed plus 8x plus 16 is x plus 2 times x cubed plus 8. Well, x cubed plus 8 gives us a sum of cubes factoring opportunity. X cubed plus 8 is x plus 2 times x squared minus 2x plus 4. Well, putting all of this together, we see that our original fifth degree polynomial is actually the same as 3x times x plus 2 times x plus 2 times x squared minus 2x plus 4. Okay? Now, we've, in the second last line, we now have a nicely compact factored expression equal to 0. One of those factors must equal 0. Let's start with the trinomial. What if x squared minus 2x plus 4 equals 0? Well, we can't factor it, so we use the quadratic formula. X could equal -b plus or minus the square root of b squared minus 4ac all over 2a. When we use that, we end up with a -12 underneath the square root symbol. Well, we realize that we can't solve without delving into complex numbers, which is in a future lesson. And this question did not say x is an element of the complex number system, which means we can assume we're only dealing with real solutions. So that factor, this one right here, x squared minus 2x plus 4, that does not provide us with any solutions. So we're going to have to focus on the other factors of 3x and x plus 2 quantity squared for our solutions to this question. So if 3x is equal to 0, x is 0. If x plus 2 quantity squared is equal to 0, x is -2. Those are our only solutions.